Today we have the seminar by Professor Neeraj Gupta from the Intra-University Center for Astronomy and Astrophysics that is in Pune, India. So that is going to be about MALS and about the MALS survey. So you can start now, Neeraj, please.
Thanks, Edwin, and thanks for inviting me. And good afternoon, everyone. It's Friday afternoon, so I'm very excited to talk to you about this MeerKAT Absorption Line Survey. And I think the way we will do this is that since it's a small group, we can keep it more interactive. And in between a couple of points, I will stop. So and we can take a few questions. That's right, Edwin. We do it that way. So
Yeah, that
the
is.
MeerKAT Absorption Line Survey is a large project running at the MeerKAT telescope, and its primary objective is to search for cold atomic and molecular gas in and around galaxies. And this is our team, which is geographically distributed, bringing in a lot of expertise that is required to carry out this project. And for this audience, MeerKAT needs no introduction. I will just quickly highlight some of the connections between MeerKAT and MALS and how we have optimized this survey to take advantage of the MeerKAT telescope. So as all of us know, MeerKAT is the most sensitive telescope at centimeter wavelength situated in South Africa, and its remote location and the specific array configuration allows us to have radio very less radio frequency interference and also excellent surface bright sensitivity to image a broad range of structures in the sky. For MeerKAT Absorption Line Survey, we are using two receivers. One is the L-band receiver that runs from 900 to 1670 megahertz, and the other is UHF band receiver, which runs from 580 to 1015 megahertz. And in this survey, we are targeting two main spectral lines. One is the H121 centimeter line, and another is the OH1667 megahertz line. So if we take the rest frequency of these two transitions, then with these two receivers, we are able to cover redshift range of 0 to 2. And I will highlight why that is an interesting redshift range to cover. And MeerKAT telescope allows us to cover both the bands instantaneously, and the correlator allows us to have approximately 32K frequency channels in the entire band. And what this means is that when we are carrying out the survey, then we have got a spectral resolution of approximately 5 kilometers per second. And that's something very important because it allows us to detect weak lines as well. And so moving on to tell you a little bit about the history of the and main specs of the project. So MALS consists of 655 hours at L and UHF bands. And we are observing 10 discrete pointings across 400 discrete pointings across the sky. And commissioning and science verification for the survey was carried out during 2017 to 2020. And actual survey observation started in June 2020. And as of now, all the 400 L-band pointings have been observed, and I will show some of the results that are coming out from this, and all because all the data and everything has been processed for these. And then approximately 240 UHF band pointings have also been observed. So all the data that we bring in from the telescope and is processed at IUCAA. And with the setup that we are using at MeerKAT, 1 hour of observations leads to 1 terabyte of data. This means that for this entire survey, we get raw data equal to 1.6 petabytes, and total survey storage requirement, if you also include all the images and spectral and cubes and everything that we also need to assemble to make public data releases, then it amounts to something like 8 petabytes. So now let's talk about what is the primary science objective for MALS. Starting from the left panel here, this is what is plotted here is the star formation rate density of the universe. And this is very well known observationally that it increases steeply over this redshift range 0 to 2 and falls off after that. And this is the redshift range 0 to 1.5 or 2 here, which MALS is covering. And this is of particularly very interesting for this reason as following. Like if you look at galaxies, if they have to sustain the star formation rate that is being observed, then they have to continuously acquire accrete gas from circumgalactic medium and the intergalactic medium. And this gas, when it comes into the galaxy, then it needs to be cooled. It needs to be then converted into molecular gas so that it can actually form stars, because stars essentially form from the molecular gas. Now, if in the third panel here, if we look at how the H1, which we would think as the most abundant element and the main reservoir for star formation here, then it's actually not evolving much over this entire redshift range. But if we look at on the extreme right panel, the molecular gas actually showing the steep evolution, right? So, in terms of broad picture, like the connection between star formation rate density and molecular gas is looking reasonable. But at the same time, there are a lot of open questions related to how the gas that has been accreted, or this atomic gas, which is sitting in the galaxy, gets converted into molecular gas and actually then form stars. So through MALS, by observing H1 and OH lines in absorption, we can actually trace the cold component of a neutral hydrogen. And so this is the intermediate phase between hydrogen gas, atomic gas, and the molecular gas that is will then from the fuel for the star formation. Another thing to remember is that cold atomic gas is always accompanied by dust. So whenever we are trying to address this science objective, we need to ensure that our observations are dust unbiased. And this is something which is taken into account even in when people carry out similar observations at optical and ultraviolet wavelengths. But radio wavelength, this becomes a definite advantage, because here we have much longer wavelengths, so they are not affected by dust extinction. So these are some key advantages and the main primary objective of MALS. So now let's look at how an absorption line can be used to study galaxy evolution at large. So let's consider this configuration where there is a distant AGN. Let's assume it to be at high redshift 0, redshift of 2 or 3. Then light from this is passing through the universe. And on the right-hand side, there is this observer. So if there is nothing in between, then we would just see an AGN spectrum shown below with only these emission lines and some continuum corresponding to AGN. But that is not the case. As the light passes through this space, it actually passes through intergalactic medium. So there are low density photoionized clouds. And then if it also happens to pass through some dense clump which is close to a galaxy, then we will also see this very strong absorption line as shown here in the damped laminal alpha absorber. And this gas can be enriched because of the star formation that has taken place, and supernova have enriched the intervening medium. Then we would also see corresponding metal lines, which are also seen in this spectrum. So this is the kind of information that the spectrum of a distant quasar can bring in. It can tell us about what kind of gases they are associated with the galaxy, what kind of metals it is. But it is nevertheless a single sight line, right? We cannot actually connect it to galaxy population at large with this. So what we need to do when we are using this as a probe is to observe large number of such AGN, so that we can do this exercise in a statistical sense. And how do we then carry out or optimize such a survey to get best scientific output? So there is this equation here, which is shown, and I want to highlight just a couple of elements here, which is that if we want to maximize our throughput for a spectral line survey, then in the middle here we have this cosmological term, but there are essentially two quantities that we need to maximize. One is the redshift coverage, which means that if my receiver is there at allow me to cover redshift Z1 to Z2, then I would like my AGN to be well beyond, so that the entire redshift range is available to me for do my spectral line observation. And second thing is this G term, which is sitting here. It represents that because my receiver will have actually a non-uniform sensitivity, right? So this means that in a certain part of spectrum, I will have better sensitivity to detect an absorption line compared to in other parts. So this is the part that is being taken care of by this term. So we need to essentially pick objects which are at higher redshift, which are also very bright, so that we have very good optical depth sensitivity. And then of course the telescope itself should be sensitive enough, which in this case is MeerKAT. So that is taken care of as well. So why do we think that if we carry out such an observation or survey with MeerKAT, then it can actually be very exciting or fruitful? That is because previously people have carried out such observations with telescopes with very narrow bandwidth, which means that delta Z has been small, and also they have not been as sensitive as MeerKAT. And of course, like they were also situated in locations which had got a lot of RFI. So due to all these factors, MeerKAT has certain advantage, and also since we are carrying out it as a large program, this means that we are able to observe objects of the order of about 100,000, which are suitable for spectroscopy. This means that we will have a uh, redshift path, which the term that I'm describing here is at least 10 to 100 times more than anything that has been tried before. So it's that this kind of jump which will allow us to obtain unprecedented constraints on the CNM factor of the galaxy, like that how much or how affect well the cold gas cross section of galaxies is evolving. So now let us just look at like how we can. So I told you that we are observing close to 400 to 500 pointings, but how do we decide which parts of the sky to look at? So this is so here onwards. I will show all the data that is actually coming from our project because the survey has been underway now for approximately 4 years. So this on left-hand side is a MALS pointing, and it has approximately 4,000 radio sources detected in it. You can see that it's full of radio sources in that. And on right-hand side, I am showing like how the RMS actually is varying across the pointing. So we, of course, because of the telescope, this response, the RMS is going to fall off as it goes towards the edges. But at the same time, you can see that the RMS is also higher at the center of the pointing. That is because each miles pointing has been centered such or selected such that there is a bright source at the center. And by bright, I mean in this case that it is brighter than 200 millijansky at 1 gigahertz, because that will mean that we will have very good optical depth sensitivity towards this source. But then there are also these additional sources which are fainter, which will not be as sensitive, but they will still be sensitive enough to actually probe the gas which is higher column density or has colder temperature. So this is the basic picture that we do keep in mind, that we have single pointing with large number of sources, brightest at the center, and through these multiple sources in the pointing, we actually get one of each one of these give us one sight line, which is like blindly searching the entire volume which is there in this, right? So then what kind of advantage we can get out of this? So again, let's look at the right-hand panel here. Here, what we can see is that the various symbols actually show what has been actually observed in the past, right? What kind of observations that people have carried out. So approximately 500 such objects has been observed. And with MeerKAT, we are now able to, as part of MALS, we are able to target more than 100,000 objects. And these curves then show actually the total power or the 1.4 gigahertz luminosity of the objects or the AGN that is being tracked by this survey. So you can see that entirely new parameter space that is being tracked here. Then how do we select these objects? Because if I say that I'm going to observe 500 pointings in the sky, and of those there are they will all be centered at 200 millijansky sources, and then there are if you look at the entire sky, there are about 15 to 20,000 such objects which are present, all scattered over the sky. So which ones to look at? So as we were talking a short while ago, we would like to have objects which are actually at high redshift. But how do we select them? If we rely completely on the optical spectroscopy, we know that optical and ultraviolet bands will be affected by dust. So what we have done for MALS is that we have actually selected these objects or these AGN on the basis of Weiss colors. So Weiss colors actually also, these infrared colors also allow us to actually statistically select objects which are preferentially at high redshift. So this wedge that we are seeing here is actually is very good for selecting which are objects at redshift greater than 1.5 or so. So we identified several thousand candidates in this range, and then using those candidates, then we carried out optical spectroscopy with SALT and not telescope. So this was a large program which we carried out uh, uh, during 2015 to 2020, and identified close to 600 objects that now actually represent from which we can select MALS footprint. So this is how MALS footprint eventually now looks like. So we have, so each plus here is like a pointing or a candidate, and then the red circles represent the ones which have all actually been observed. And you can see that there is also a very nice overlap with some of the large surveys like DESI and Foremost. And this has been done because eventually optical spectra are very, very useful to carry out uh, effective science, because whether it be in continuum or in the context of spectroscopy, it's useful to have multiple species detected, or know how this object looks at multiple wavelengths, then because then we can really understand what kind of physical conditions are prevailing there. So for this, then all the serendipitous objects which are there in the pointing, a lot of them will have a spectra from this, and this will allow us to do our science efficiently. So I think this is one good point, Edwin. We can stop and take a few questions if there are. I can also slow down a bit if needed at this point. Because after this, I'm going to talk about how we actually process this data. So that itself is also a big challenge.
I do have a question. So you put
Mhm.
the noise for pointing, but for radio continuum. What is the noise that you need per channel to get a detection of the
Yes.
absorption?
Yes. So I will. So let me go through the next few slides, and where I will describe processing, and I will also describe noise properties of various data products.
Okay, perfect. So if there are no questions, we can continue.
I had a quick one.
Okay,
Hi,
go.
Tony.
Hi, Neeraj. What is the NOT telescope?
What is the NOT is the Nordic Optical Telescope, actually.
Nordic Optical. Okay, thanks.
Yeah, it's a Danish telescope.
Okay.
It's a small 2 meter class telescope, but it has got a very good back end, because of which it's like actually really works very well, actually. So our strategy was that since we have a distribution of magnitudes for objects, so the ones which were brighter than 19th magnitude we observed with NOT. So about close to 100 of them, and then around 300 of other objects we observed with SALT, actually, the fainter part of it, like magnitude
Okay.
20th or 21st. So that was the strategy we adopted. Because with one telescope, it takes much longer, basically. Yeah.
For sure. Okay, thanks.
Okay, we can continue.
Okay, so now let's look at, like, if the data, as I told you, that it's 1.6 petabytes we are getting from the telescope, then how is it that we can process it effectively? Because it's a lot of data and can take a lot of time to process. So let's these observations, like 400 pointings at L-band, 400 UHF, and like we can round it up to 1,000. They are being observed over 5 years. So a simple thumb rule or the strategy would be to actually process each pointing to create all the data products in approximately a day, right? Because that means, like, roughly we are talking about 3 years, but with certain latencies involved and certain efficiency factors, you can imagine that this would spread out to 4 to 5 years. So that's this the thumb rule that we use to size up the computing that is needed for the project. And what are things that we need to generate? Of course, we need to first calibrate all the data and calibration, and then all the flagging needs to be done as well. And then once this is done, then the data is ready for imaging. Then we need to create continuum products, which is like continuum images, the kind that I had shown to you. And then along with this, we also need to make the spectral line cubes, of course, right? And the spectral line cubes is like is a large cube in which every frequency channel has been imaged. And if you want to do polarization, then we need to do full Stokes imaging, which make like these continuum images for I, Q, U, and V. So the typical RMS noise that we are getting in our continuum images is like for is close to 10 to 20 microjanskis, and when we make spectral line cubes, then per channel RMS is approximately 0.7 millijansky per beam. And both these numbers I am quoting are for robust is equal to 0 weighting in CASA. So that's the kind of RMS noise we are getting. And this is just a quick overview of like the setup that we have at IUCAA. So this volume of data and generation of these many data products cannot be done in a manual fashion. So to keep track of it, what we have done is we have set up what is we call as automated radio telescope imaging pipeline. So it takes care of not just automated processing, but also archive and analyzing, and also designed to push the products into archiving environments such that we can make public data releases, because that is extremely important, because with these many large number of sources and spectra in place. We will, as a team, of course, do some science, but then there's a lot of science that can be done by community over in future, right? So that's so details of this pipeline are available at our website, and also like in this paper. We can also talk about it in detail later in my talk. And here what I'm showing is like some idea of like how do we actually, or what kind of products we generate. So calibrated visibility is, as I said, like 1.7 petabyte is the raw data. So we get another 1.7 petabyte when we calibrate it. Then spectral line cubes, so 32 channels at L band and 6K by 6K images. So that's like huge terabyte size cube, but we break it into 15 chunks because that then allows us to sort of parallelize the whole thing on different nodes. And so 4 million core hours is essentially the total compute that is being going into imaging these. And in terms of storage, we have, as I told you, that everything will require something like 8 petabytes. So we have a fast storage of 4 petabyte, and then 2 petabyte of disks, slower storage, and then another petabyte. Now cluster has got approximately 26 nodes in place. So all the details are available at our website in case you want to look at it in more detail. So this is my summary up to this point. Like we have we have defined a survey footprint, which is like optimized for the survey, and then is also nicely overlapping with various large optical surveys that are coming up. And since we need to also process large volumes of data, we have also set up this computing infrastructure in place, which is not just going to generate all the products, but it also will push them such that it can actually be available for the direct release, for the public data releases. So now rest of the talk, I'm going to talk about science results. So maybe this is another point where we can stop and maybe take a few questions, Edwin.
Okay, questions? Mm, mm, no, I don't have. I think we can continue. I don't have questions. We don't have.
Okay, so but Edwin, I answered your question, right? You asked about the RMS part. That is
Yes,
verified,
thanks.
right? Okay, great. So let's now proceed. So I will talk about early science, and then I will move towards survey science and data releases, right? I'm really keen to spend a little bit of time in describing data releases, because that is something publicly available and people can use it very well. So this is the first spectrum that we had taken with MeerKAT. This is a 10 Jansky source, very bright source. So Tony, this is the exact source which I have also proposed as one of the targets for HireX, actually. So this will be of interest, double interest.
Yeah, it
to
looks
us now.
familiar.
Yeah,
Yeah, for sure.
So there are 3 panels here. First panel is actually, it corresponds to UHF band. You can see it runs from 560 megahertz to 1060 megahertz. And then the subsequent 2 panels are showing the L band going from 870 megahertz to 1660 megahertz. And we chose this particular target because it is very strong. And it has actually 2 absorbers which are already known. One is at a redshift of 0.19. and another is the redshift of 0.89. So these circles represent some of the absorption lines that were known in past. So idea was that, okay, we observe this known target, and then with that, we do science verification and see how well we are able to recover the known physical quantities. But the fact that MeerKAT is so supremely sensitive compared to anything that has existed up to this point, we also detected some of the weak lines corresponding to OH lines, satellite lines here, which were not known before. So, and you can also see that like the spectrum is of such excellent quality. These alternate colors that you are seeing here in the spectra are corresponding to different frequency chunks. As I told you that instead of making a single 1 terabyte huge spectral line cubes, we break it into 15 chunks, entire UHF or L band bandwidth, because this then allows us to parallelize, and also the data product that comes out of it becomes easier to handle, right? Because 1 terabyte is just unnecessarily large in this case. So this is zoomed in version of the satellite lines that have been detected. You can see like very weak but very well detected here in the spectrum. And so this quasar actually shows not only lines of centimeter wavelengths, but it has also been observed with ALMA, and it shows these very nice lines in molecules of HCO plus, CH plus, and H2O. And when we are looking at an AGN over such a large frequency range, in this case, starting from half gigahertz going up to, let us say, 100 to 200 gigahertz, then the background AGN itself, the radio continuum associated with it itself, can be very different. So if we look at these two panels here on the top left corner, you can see that this object looks like these compact clumps at ALMA, very high frequency. But when we come to low frequency, you can see that like there is a lot more diffuse emission that is associated with it. So there's an Einstein ring. That's why you are seeing it as a circular thing here. So using these different continuum emission models at different frequencies and the velocities of the spectral lines that have been observed, we were able to model the distribution of gas that is present in this foreground galaxy quite consistently. So this is a very nice example of that, how we can actually combine our data at different frequencies and determine the properties of gas from which the absorbing line can be originating. This is another first from MeerKAT Absorption Line Survey, which is that this is what is showing here is the first unambiguous detection of distant hydrogen radio recombination line. This is a shift of 0.89. And this is very exciting because the survey is primarily targeting H1 and OH lines. But with the radio recombination lines, we also get an access to look at how the ionized gas is evolving. By this, that using few selected sight lines from the survey, we can actually also put some constraints on how the ionized gas may be evolving as a function of redshift. This will be an independent constraint coming from a radio survey. So now let's go to really low redshift, that is the L band closer to 1420 megahertz. What we are seeing here is the field of a QSO. This comes from actually Cubs survey, which is being is a project being carried out with HST telescope, and we have observed the common pointings with MALS. So this one particular quasar, the zoomed in version is shown in the central panel here. And we can see that this QSO, and there are these two galaxies there, G1 and G2 marked here. And if we just look at the optical image, we will find that there's hardly anything going on here. And this quasar actually shows a very strong absorption line. This is the absorption line of lamina alpha in the HSC spectrum here, right? And this is coming from this dwarf galaxy. So by looking at this, we can just say that this gas may actually be this absorber may actually be associated with the extended disk of the damped lamina absorber. On the extreme right panel, what we are seeing here on the top is actually how this field actually looks in H1 emission, because MeerKAT is sufficiently sensitive that from the nearby galaxies, we can actually serendipitously also detect H1 in emission and not just in absorption. And by looking at these contours, you can actually make out that these two dwarf galaxies are actually interacting with each other. And from this, we were able to infer that actually the gas that we are seeing in absorption is actually the gas that has been pushed out of the galaxy by interaction. So this is again another nice example of how we can actually combine observations of radio and ultraviolet wavelengths to actually then determine the thermal state of the gas and how it may be related to the galaxy. This is another example, now going to very high redshift, 1.3. This is actually corresponding to UHF data. On left-hand side, the panels are showing the radio continuum image. You can see two sets of contours because we have shown radio images at 1.4 gigahertz as well as also at UHF. So just the radio source itself is compact, but the synthesized beam is evolving. That's why we see like that the same source is having two different sizes. It's just because of the resolution being coarser at lower frequency. And this is the SCD. We can see it's a nice steep spectrum. And then this is the nice absorption that has been detected at a redshift of 1.3. So this is now we are seeing gas associated with the AGN itself, right? Because when we look at an AGN and the cycline, the light that is coming from it can also be absorbed by gases actually associated with the AGN itself. That's what we are seeing here. So that one would say that nothing surprising here, but on the extreme right, if we see, we can, what is shown here is the optical spectrum of it, and 0 it marks, and on the X scale actually marks the velocity corresponding to 21 centimeter absorption. And you can see that there's nothing that is detected in the optical spectrum here, right? So this is like a very nice demonstration of like there may be a situation where a lot of gas is present in the object, but it may not get completely missed in the optical spectrum, but it can be very well detected in the radio spectrum. Why would that happen? Because radio structure is actually much more extended, much more diffuse. This means that naturally it actually provides much larger covering factor, right, to the gas that is present. Where like in case of optical QSO, it's just one sight line. It may, and if there is a patchy distribution of clouds, this sight line may actually miss clouds. So radio survey can actually be a very effective way of taking stock of the total overall presence of cold gas in AGN in general. So now next, I'm going to talk about a few of the data releases that have happened and some of the upcoming ones, and then conclude. I think, yes, that's the sufficient amount of time. So we recently made first data release from MALS. This was actually late last year. And this consists of L-band continuum images and approximately 500,000 sources. So this is the associated paper presented here. It's led by a PhD student, Partha Dekka, based at IUCAA. And the bottom three panels demonstrate some of the science cases that we have addressed in the paper, but it also shows like the variety of things that can be done. So here actually what on the left most panel is showing the source counts, which shows that it's matching with the survey. It has got nice completeness for sources brighter than 1 millijansky. On the center, what we are showing here is that when we compare our project or the observations which were carried out in 2020-21, when we compare this with NVSS, which was carried out in 1996 or so, mid-90s, and much shallower, so we could compare only the brighter sources. But then we found like a few thousand sources which have actually varied quite dramatically over this period. So these could be some very interesting objects that can be followed up for a variety of science. And on the right-hand side is demonstrating the power of spectral indices. So although it's just L-band, but it is still going from 1 to 1.7 megahertz. And we can use this to estimate spectral indices. And on x-axis is chopped here, but x-axis here is actually flux density. So it is going from left-hand side, extreme being like 0.5 millijansky, and then goes up to like the brightest of like a few hundred millijansky. And what we are seeing here is through these curves is that the spectral index is actually of the objects with the flux density is flattening. So why this? So what this implies? This implies that as we are going towards the fainter objects towards the left hand, the underlying population that is there of these radio sources is changing. And one simple explanation could be that as we are going towards the fainter objects, we are actually probably looking at more FR1 types of sources which are more dominated, so they will have flatter spectral indices compared to the FR2 sources, which are more lobe dominated. So this is something which actually can be confirmed using high spatial resolution observations to see if the distribution of FR1 and FR2 objects itself is changing. So this is another example of the kind of science that can be done with such large survey. Of course, our interest will be to take a population of these objects and then do spectroscopy or 21 centimeter search within them and see like how the cold gas itself is evolving in these populations. So that's what would be our idea. So all these data products images are available from our website. You can explore, and you can also download objects of your interest. You can also download images corresponding to full pointing. Such bulk downloads are also available. You can go to the website and actually explore and see what you would want to do. So this is the second data release I'm going to talk about. This is the beta version is already available. We will soon publicly announce it with the acceptance of the associated paper. It's led by Jona Wagenwald. He is a PhD student based at Max Planck Institute in Germany. So on the left-hand side, what I'm showing here is actually this view graph is actually taken from a paper by Ray Norris, and I have pasted on it like where we stand for MALS. So x-axis is just the year, like 1940 starting 2020 plus here, and then y-axis is logarithmic in source counts, right? You can see the number of sources over the years have increased, and MALS, you can see with MALS we are now currently standing at about 1 million, and when we finish we may be actually finishing at a few million. So like really comparable to large surveys, and with this like a lot of variety of science goals can be addressed. So this particular data release will have close to 1 million sources here, and one can also do some interesting cosmology with them. And what would happen early next year is that we would also provide UHF images from these pointings as well. So because we have been receiving a lot of requests from the users to provide UHF images as well, because then we would have these really nice wideband spectra for this variety of sources. So now I'm moving into the core science, which is related to the spectral lines. This is the data release 3, which will be happening sometime later this year. So what is this? What this contains actually? So I've told you about all these AGN, which are at different redshifts in the point field of view. There are like several 4,000 sources, and out of these 4,000, about 100 to 200 sources are also bright enough to do spectral line science. But all these sight lines that are coming from the AGN actually will also pass through our galaxy, right? So this is also a very nice experiment actually to look at how the gas in the Milky Way halo is distributed. So what is shown here is actually the H1 emission map on this top left panel, and each circle here represents a pointing here, right? So I will skip what is the meaning of different colors, but you can see that like there's a nice distribution of this pointings probing like very interesting regions of the Milky Way. And on the right hand side, I show some of the spectra. You can see that some very nice spectra has been detected. So we have developed now an analysis package which can automatically search for absorption lines in MALS spectra and model them and derive physical quantities, because we are talking about searching, in this case, for example, searching for 20,000 spectra. And out of this 20,000 spectra, 3,500 absorbers have been identified. And if you look at this bottom panel at left, you can x-axis here is the distance from the pointing center, because I've been telling you that like there is this large field of view and sources all over the field of view, and we can detect absorption in them. And you can see that this hashed histogram is actually showing the various absorption lines that have been detected here. You can see that like there is detection over entire field of view. Why is that happening? Because even though sensitivity is falling off as we move away from the pointing center, but for absorption line, the sensitivity essentially comes from what is the brightness of the background source. So if there is a 1 millijansky source at the pointing center, and let's say 10 millijansky source far away from the pointing center, the 10 millijansky source may actually have much higher optical depth sensitivity because it is intrinsically bright. So that's one of the very nice strength of absorption line spectroscopy. So there's a nice proof of concept also that we can actually detect absorption lines over the entire field of view. And on the right hand side, what we are seeing is how the detection rate is changing as a function of optical depth sensitivity. So this field histogram is showing where all the detections are, and you can see that like detection rate can be as high as like 80% at when we are talking about like really a sensitive end of our survey. But as we go towards lower sensitivities, the detection rate also falls off, and then at some point like there are no detections here. So this is like a nice exploration of the parameter space. But all this is done keeping in mind that the places where we don't have direct individual detection, we can actually do the stacking and then recover some of the physical properties still, right? So this is one. So to give you a little bit more flavor of what kind of science that we can do once we detect these kind of absorption lines. So let's look at this plot on the left. What we have here is actually y-axis is integrated optical depth for each absorption line that I was showing here. And on the right hand and on the bottom panel, there are two things that are plotted. On these blue symbols that we are looking at are corresponding to NH1, that is H1 column density, that is measured using H1 emission. So you can see that blue points are following this particular dashed line. And on for the this yellow symbols are corresponding to same absorbers, integrated optical depth is same, but x-axis is now replaced by dust extinction, which is measured using far infrared map of the sky. So you can see that like in up to this range, like less than 21 per centimeter square in column density, in terms of for extinction, it will correspond to 1 magnitude extinction. Actually, these are following pretty much the both red, blue and yellow points are following actually the same. They have the same trend, same slope. But as we go beyond this, they actually diverge. So what's happening here? So up to this point, what is happening here is that the total H1 is actually being perfectly traced by H1 21 centimeter emission. But as we go here beyond like 1 magnitude or higher column densities, then a part of the gas is actually being converted into molecular gas. So this is the onset of molecular formation that is being taken place and leading to this turn over away from this trend, which is being corresponding to the blue points. So this is a very nice demonstration of how we can actually derive physical conditions from absorption lines when we combine them with complementary data. And the right-hand side is actually showing, so each pointing has actually these multiple sight lines, right? So if I detect an absorber towards one sight line, I can ask the question that whether it is also detected towards the other sight line or not, right? So y-axis is showing here the difference in the optical depth towards the pairs of sight lines, and x-axis is showing the separation. And this is something that has been done for all the pointings. So you can see, so it looks very noisy, right, in the way, but we can do some statistics here and try to determine that how actually the difference in the optical depth between these pairs is changing with the separation. And now the magnitude of this and the scatter of this actually is depends on what kind of the structure of clouds that is present in the ISM, and or like the kind of turbulence properties that are prevailing in the ISM. So these are the things that can be constrained by these very simple observations that we make by just take one spectrum here, one spectrum there, and detect an absorption line, right? So this is why this is interesting, even though it is for galaxy, because even for galaxy, these kind of things are not very well done, because what the kind of plots that we are seeing here actually consist of thousands of objects here, right? Whereas like the best of the surveys up to this point have actually looked at like at 100 objects or so, right? So the determination of physical quantities is much more robust here, and also we can actually do a much better exploration of the parameter space. So idea here is that we use our galaxy as a template to determine CNM fraction, filling factor, and the structure of these cold clouds. And this template then can be used to interpret the extragalactic absorbers, right? Because when we look at something at redshift 1, we have, how do we interpret it? What does it mean? So that framework can actually come from our galaxy because it's nearer, so we can look at it in more detail, right? So coming to this another data release, which is 4, this will be happening early next year. And this is actually, will be focusing on the L-band extragalactic spectra that we are, which are tracing cold gas with AGN or with the intervening galaxy. These are some of the examples that I'm showing here. But I'm not going to talk about those results here today because I have a talk in IAU symposium. This will be happening in 13 to 15 August, and I'm sure all of you are very excited about it. And I hope most of you will be there as well. And I'll be presenting first results from this in that. So if you're there, like please come. And there are a lot of very exciting talks in this symposium talking about how H1 is evolving in and around galaxies. So those are the results I'm keeping for that special symposium and talk there, right? So this is my summary of the science that I presented. Started with like some of the exciting results that have come out of individual objects, then the survey science corresponding to Milky Way galaxy, and then there are these various data releases that I have described. And first 2 of these are already available. You can start using it, and then the remaining of them will come. L-band this would finish maybe by mid next year, and after that, most of it will be the UHF data. So there's a lot of science that can be done by everyone here. And this is the summary of my talk, and I will stop here now, and then we can have a discussion and questions.
Okay, Neeraj, thanks for the seminar. Very interesting. So maybe we can have some questions from the participants. Otherwise, I have a question about the quasars and the 2 satellite galaxies. So the contours that you see in the image, maybe you can go to the slide because I didn't get what were the
Yeah.
contours.
Let me share. Yeah. Yes. Yeah. This one?
Yes, with the contours. Yes, these contours are is radio contours or
Yeah. These are contours of H1 emission, H1 21 centimeter line emission. So we can integrate it. So this is the moment zero map of H1 column density.
okay. So okay, you have the Muse image, so you know the detail. Okay, I get it.
Yeah, the Muse is the actually bottom one that is showing H alpha.
I'm using a sensitive enough to try to get the space between the two galaxies
Oh yeah.
to see if there is a more gas between in the intercluster medium or whatever they are located.
This is the group intragroup medium actually. Yes.
Okay, intergroup medium. Okay,
So
okay.
this
Yes,
quasar
that
is
was
at background, and these galaxies are at redshift 0.026, and this quasar is at redshift of 1.3. So this quasar here is actually tracing the gas here, H1, which is actually giving rise to this deep absorption in the HSC spectrum.
okay. Okay,
So that's the
thanks.
configuration. Yeah.
Okay, more questions? No. So we
I had
can.
one.
Okay, yes, Tony, please go ahead.
It's actually about calibration. She was talking. What calibration steps do you do? Do you do direction dependent calibration in this? Or?
So up to this point, all the data releases are without direction dependent calibration, and from mid next year onwards, we will have releases which will also do direction dependent calibration. So the idea is
Okay.
that direction dependent calibration actually introduces additional degrees of freedom. So we want to first create all the catalogs and images without those corrections so that we can track any systematics and errors that come into play with that.
I see. Okay. So, thanks.
Yeah,
Okay,
because
we
like, for
have.
example,
No, we have another
yeah, so
question,
you
but
see that with the large survey, even these small effects become very detectable, right? For example, the right-hand panel. So we have to really understand that when we are going into these additional corrections, then we don't really introduce any effects which actually change the properties of source in a systematic way as a function of distance from the pointing center, for example.
Okay. Thanks, Neeraj.
Or close to strong sources, right? Because that's what direction dependent correction would do. It will be weighted in some way to certain locations within the pointing.
Okay, we have another. Thanks, Tony, for the question. We have another question by Tanita.
Hi, can you hear me?
Hi. Yes.
Great. Thank you very much for your talk. I have a question about the science you're doing on the Milky Way. And wondering how you're interpreting the H1 that you're seeing. Yeah, exactly. For like, can we interpret these as like infalling or outflowing gas from the Milky Way, for example, and whether they're linked to like high velocity clouds? I don't know.
Yeah, so if you look at the velocity distribution of so there are a couple of things to keep in mind. One is that when we look at the distribution of pointings here in the top left diagram, we can see that like we are generally at a slightly higher latitudes, right? And that's coming from the design of the survey itself. So we are not really looking into the disk of the Milky Way. And then at this high latitude, when we're detecting these absorptions, then most of these are actually within plus minus 50 kilometer per second in LSRK. LSR frame. So we are at best going up to intermediate velocity clouds. That's what we are seeing, not really high velocity clouds. And to a large extent, we are even probing mostly the local interstellar medium, that the inside the bubble,
Thanks.
basically. Yeah.
That's cool. Thank you very much.
Okay, thanks, Anita, for the questions. More questions? No, otherwise we can say thanks again to Neeraj for this very interesting seminar and all the exciting results. So, so thank you very much again, and thanks everybody for
Thank you.
coming.
Yeah, I really enjoyed. Have a nice weekend.